Oh, thanks. Have to hit the go button.
Okay. I'll let her know. Should work now. Okay, yeah, I said it was waiting for us, so we should be good now.
Okay.
Okay, any other comments or?
Always on public astronomy nights. We do need the help running scopes on the pad and so forth.
Or just even people in there just to point to the bathrooms and make the coffee, either way.
Yeah, unfortunately, in our most recent one, I think the weather didn't help us much. It was pretty cold that night. And I
Yeah.
think that kind of discouraged people because I don't think we had anybody.
No, we
Negative
didn't.
wind chills, I can't
By the time
believe.
we left.
Which was too bad because it was a nice clear night,
yeah.
but it was also pretty cold.
Yeah, we saw both of the space stations go over. It was kind of neat to see them both, the Chinese and the ISS.
Yeah.
That's always fun.
Okay, one other thing, and this is mainly for board members. I sent out an email about this earlier, but just, as some of you might know, Astro League has been redoing its bylaws, and of course, we're a member of it, a member club. So, I've been involved a little bit in the process of revising these bylaws, which has been very painful, to be honest with you. But now they're done. They're ready to be voted on. So those of you, this is mainly probably a question for those of you that are board members. Should I just go ahead and vote on behalf of the club, or does anybody want to see the changes?
I think Dave was the only one.
Dave mentioned that he was wondering if there's an attachment, and I can send them around. The vote's not due till March 31st, so there's a little bit of time if people want to look this over. I mean, to be honest with you, I never saw the bylaws before the changes, so I don't know, except most of the changes are grammar and,
Parliamentary.
there were long discussions about whether to use a comma or a dash,
Oh,
those
for
sorts of
God's
things,
sake.
which can be, after a while you kind of wanted to scream. But there were a few things in there that I think were a little bit more substantive. But in any case, I can go ahead and circulate that to board members if you're.
Yeah, I'd like to see it.
Okay, I'll go ahead and do that then. Okay, that was one thing I wanted to talk about. I did have a couple of more things that I just wanted to mention. First of all, today is World Meteorology Day. I mentioned this as an ex-meteorologist. Back in my younger days, my very first real job was as a meteorologist. So March 23rd is always World Meteorological Day. Not to be confused with World Metrology Day, which is all about measurement. But so anyway, happy World Meteorology Day. Second thing, this just caught my attention today. I don't know, we talked a little bit about this in a meeting once. This is Oumuamua, this object that passed through the solar system a few years back and did some unusual things, including speeding up, and that attracted some attention and apparently some speculation that it was perhaps some kind of alien probe. There was a whole book got written about this, which I have a copy of if you want to read it. It's the guy that wrote it is like the chair of the Department of Astronomy at Harvard.
It might have been, I don't know if he still is or not.
So I mean, this guy's obviously not just somebody that wandered in off the street, but
It was a little speculative, but it was a good book.
it was a good book. Yeah, very interesting, and I'm sure the guy would be fun to talk to, but I don't think he made his case, to be honest with you. Anyway, so a couple of
intergalactic balloon, car sales.
A couple of chemists did an analysis of the composition of it, and they figured it probably is really just kind of a type of comet, and the change in velocity was just because comets heat up and spew out gases, and then speeds things up. The reason why there was some doubt about that is apparently spectral analysis of it didn't show clouds early, but they figured these were probably very small, but just enough to get it going a little bit. So anyway, this was an article in the New York Times today. So
I think the speed increase negates that theory, frankly.
yeah,
Mm-hmm.
but anyway,
I think the increase was much quicker, much faster than what you would get from a small jet.
well, at any rate, it was
I
they
think some
kind
of it too may have been gravity assist from like Jupiter or whatever.
I don't know, that's pretty easy to calculate in, though.
yeah. But anyway, this was something that sort of caught my attention, so I kind of figured I'd throw that out there just as follow up on stuff we talked about earlier. The other thing, of course, is this has become kind of crazy. You know, last time I think we talked about measuring asteroids using penguins as a unit of measurement. Today or yesterday, I guess, there was an article, or a few days ago, there was an article about Borzoi dogs, which they're a pretty good sized dog. I found a picture of one here, and that's, you know, that thing's about waist high on probably a fairly average sized person. So these are not small dogs by any means, but so now Borzoi dogs are being used as and I saw one today that was American alligators. Was another unit of animal measure they were using to compare to asteroids. And there's an article about it, I think it was in the Atlantic, where talking about this tendency people have now to compare asteroids to things and animals now in terms of size. So anyway, we now have a new measure of size for this. Is this one that you've imaged?
I don't remember if that's, there's been several that have been close to the earth there lately, but.
Yeah.
And we image dogs occasionally.
Well, now you know how to translate at least Borzoi. I don't know, I mean, I'm not sure how that Borzoi dogs would
Getting back
translate.
to our collimation efforts, if it doesn't do well, we get dogs.
Okay, well, now we know that, how many of those dogs are the same size as
Yeah.
these asteroids.
You get sun dogs, moon dogs, now we got.
Yeah,
All
well,
kinds of dogs.
I'm actually starting to develop a collection of these little articles, because every time one pops up, it just is something new. You know. The penguin one is still my favorite, because I kind of, you know, I have a soft spot for penguins. But,
I have a grandson who does too, and you
Even
have
though
something on your computer.
they are vicious little creatures. They will bite the
Okay.
crap out of you, but at least in my experience. But anyway, so that's another piece of news that just sort of caught my attention. Okay, well, anyway, I kind of want to get on to the main event here, so I will do that. So we have a guest speaker for us with us tonight. This is Dr. Bharat Ratra from the KSU Department of Physics. He's a University Distinguished Professor of Physics. University Distinguished Professor is the highest academic honor that the university can bestow on a faculty member, so that's quite an accomplishment. So I am very excited to hear this talk. So I'll get out of the way and we'll let Dr. Ratra give his talk.
Thank you. I'll try not to embarrass you too much by letting you down.
Do you need this?
Sure.
Okay, and I'll just kind of get out of the way so you can see the expanding universe over here.
So what do I do? Just
I think,
I'll go down. So,
oh, that's, okay, let me get over to me here
okay.
and get to you. So, there we go. And I'm not sure how to do this with the
We can-
PDFs.
Should just be page down or whatever.
Oops.
Oh, Standard Mall up
Yeah,
above,
yeah.
right there.
I
There's
want
your
to
page.
get
Full screen?
full screen.
Oh, I think that's in the upper right. Up there.
Yeah, he's not used to using this mouse.
It's not here, probably good.
Yeah, why don't you do this?
I'm using PDFs to help a lot.
Is it Alice running back to?
Yeah, if you just put it full screen, that would be great. Okay.
Okay.
There you go.
Well, yeah, okay, so yeah, let me go back one page.
All right.
Okay, so I'm a cosmologist, and it's really nice to be here and talk with people. So if you have questions, just feel free to ask me, and we can do that during the talk or later on, so whatever you want to do. And it's a really great time to be working in cosmology, which is a study of the universe and structures in it, pretty large-scale structures, and how they change in time, how they evolve in time. And before I forget, can I kill this somehow?
Maybe there's an option in view.
Okay, great.
No,
That's
Um,
good one.
Yeah.
it took off the full screen.
Yeah.
Okay.
That was the only way. we'll keep
Well, we
it.
can do it this way. This is fine.
Yeah.
There's those cards that I passed out. They're kind of connected to this website, and it's a really, really nice website. They've got really great videos that explain global warming really simply. And it's a useful thing to know about because it's going to affect things quite a lot. So this is my almost my backyard. It's about 10 minutes away from where I am. It's Gonza Prairie, which is owned by the Nature Conservancy in K-State. And these are bison, they're not cattle, but it's a really, really nice place to go hiking. So I have a bunch of questions for people, and you can put up your hands as you answer them. So how many of you have gone hiking? 1, 2, okay, most of you. How many of you have gone hiking 10 kilometers in your life? 100 kilometers total? Or just
20.
one?
20 mile.
Maybe.
Oh,
20 mile run.
100 kilometers is 60 miles in your whole life.
Yeah, that's probably done.
You
Okay,
like it?
600 miles.
Yeah.
Okay, that's 1,000 kilometers, so 6,000 miles. Okay, so that's kind of an upper limit to the distance you can hike. I mean, if you have a lot of time, you can get pretty far. There's also an upper limit to the amount of time you have, and there's also a lower limit to things you can feel with your senses. So I want you to reach up and grab a strand of your hair. I mean, those of you who have hair. So just kind of reach up and feel it, and is that kind of the smallest diameter object you can probably feel with your fingers? I mean, that's kind of the limit. It's somewhere around there. So there's kind of a range that you can directly access with your senses. So a typical hair, if it's thicker, it might be 100 microns or so in diameter. If it's really thin, maybe 10 microns. So it's somewhere around over here. So this is distance in meters. So meter is roughly 3 feet. And this is typical human size. And if you have enough time, you can walk maybe 10 to the 5 or 10 to the 6 meters. So you're kind of restricted to this range that is accessible to you directly through your senses. So, but there's a whole bunch of length scales on much, much larger length scales and much, much smaller length scales. And this is the powers of 10 notation. So these are, each time you go, it's like 10, factor of 10 to the 5, another 10 to the 5, 10 to the 5 again. And so it's a really, really big jump. And you can't access any of this directly over here and here. We're very restricted to this very, very narrow range of length scales. So all our intuition has been built up on this range of length scales over here. And if you're exceptionally clever like Newton, you can bounce balls around or look at dropping apples, and you can figure out conservation of energy and conservation of momentum and Newton's second law of motion and his law of gravity. But if you want to try to do the same thing over here, you can't really touch those length scales with your hands or your feet. And you've got to use devices like, I mean, all of you know you've got to use a telescope if you want to see things really, really far away. And if you want to see things on really small scales, you've got to use particle accelerators or microscopes. And so what you're doing there is you're basically collecting light, and you're turning that into an electronic signal in a computer. And the way you do physics and the way you build up intuition on these scales and on these scales is fundamentally different than the way you build it up over here. So you take these electronic signals in your computer and you have a mathematical model of the phenomenon you're trying to study, and you use that mathematical model to predict what sort of electronic signals you should have seen. And if they agree roughly, then you're happy. If they disagree, then you try to improve your model. And eventually you build better and better models, and you build better mathematical models, and then that's how you develop intuition. So it's probably not that surprising to kind of realize that relativity, which is really important on really large length scales, and quantum mechanics, which is really important on really small length scales, don't have the same kind of intuitive feel as Newtonian physics that was developed over here and everyday physics that you deal with in your life. And so maybe it's not that surprising, but most of the world is that way. It's not Newtonian, and you can't really access it through your hands and your feet. And the intuition you develop through your hands and feet is kind of completely misleading on really large scales and really small scales. And maybe that's why people find quantum mechanics and relativity so strange. But quantum mechanics and relativity, I mean, we have mathematical models, and you can describe phenomenon, and they agree really, really well with whatever measurements you do. And so I want to spend a little bit of time kind of walking out from here outwards. And I did not coordinate this with Doug, but instead of using this old-fashioned system of units, I'm going to use this guy as my length unit. So we'll have an Einstein, which is 2 meters, so it's roughly 6 feet. And you can do this in terms of masses, in kilograms, or in terms of ages or time scales, but there's not enough time to do that. So I'm just going to focus on length scales. And if you're interested, there are 2 really, really good videos you can find on the internet now. One's called The Powers of 10, and it's by the Eames brothers. And they're architects, and it's a really beautiful video. You can kind of scan out in large scales and down to small scales. And the American Museum of Natural History has an updated version of that that's also really, really nice. I'm not sure what the name is, but I think it's called Powers of 10, and if you put in American Museum of Natural History, you'll find that. So we're going to start out on this scale. And we want to look at the small planet, the one we live on. We can get pictures like this. It's only been possible in the last 60 or so years. This is Madagascar, it's the Horn of Africa. And to get some idea of the sense of scale, maybe you can do an experiment, or at least a thought experiment. You can drill a tunnel from the North Pole to the South Pole, and go to a store and buy Einsteins, and you'd have to buy 6.5 million Einsteins. You put one at the South Pole, the next one on his shoulders, the next one on his shoulder, and the next one on his shoulder, and you need 6.5 million Einsteins. So it's roughly a factor of 10 million to go from human scales to the scale of a small planet. We can go out and look at a bigger object near us. This is the sun. And you can do the same thing. Maybe the easy way is, I mean, well, you can't really drill a hole through a bunch of gas, but you can take 100 Earths and pile them up one on top of the other, and that'll give you the diameter of the sun. So it's a factor of 100 going from the scale of the Earth to the sun. And if you want to do this in terms of Einsteins, it's 700 million Einsteins. So you need a lot of them. We can look at a few other numbers. So the Earth goes around the sun, and it's approximately a circular orbit. It isn't quite, but it's an elliptical orbit. But if you average it out over the course of a year, you can get an equivalent circle. And the radius of that circle is the distance between the Earth and the sun, an average distance across the whole year. And we could use meters to describe that, but you're getting these many, many powers of 10. And so people who study solar systems and extraplanetary systems, exosolar systems, they don't like using meters for their length unit, and they use 2 different length units. So one's the astronomical unit, and the abbreviation is the AU, and that's just the radius, effective radius averaged over the course of a year. The other unit they use, which is probably a little more useful for physicists, is the light travel time. So light in vacuum has perfected cruise control, and it always travels at exactly the same speed. And that speed is pretty large. It's 3 times 10 to the 8 meters per second. And there's an easy way to get some idea of the sense of the scale here. So a meter is roughly 3 feet. So if you replace the meter by 3 feet, you get 9 times 10 to the 8, which is roughly 10 to the 9, which is a billion. So you can think of it as a foot. This is roughly a foot. So light takes a billionth of a second to travel a foot. That's a nanosecond. Or in a second, light travels 1 billion feet. And it goes really, really fast. So we can take the speed of light. I mean, you do this all the time. So if you say you're going from here to Kansas City, which is probably, 70 miles, and you set your cruise control at 70 miles per hour, it takes you 1 hour to get to Kansas City, and you don't have to say that Kansas City is 70 miles away. You can say it's 1 hour away, and that's a measure of distance. And you can do the same thing with light. So if you divide this distance by that speed, you get 500 seconds. So when you look at the sun, and all of you know you shouldn't look at the sun without protective equipment, but when you look at the sun, you're seeing light that was emitted from the photosphere 500 seconds ago in the past, and that light traveled in a straight line, and it hit your retina and got converted into electrical signal, and your brain made that image of the sun. But you're not seeing the sun the way it is now, you're seeing it the way it was 500 seconds ago in the past. And you can't see anything now, it's impossible. So even when you look at the person next to you, you're not seeing that person right now, you're seeing that person maybe 1 or 2 nanoseconds in the past. And your brain's not sensitive to that, so you kind of assume, because you're kind of used to all this Newtonian physics stuff that happens at very, very small speeds. You're assuming you're seeing the person right now, but that's not true. You're always seeing the person in the past. And that becomes more obvious when you go out to much, much larger scale. So you're seeing the sun 500 seconds ago in the past. And so we can step out to the next nearest big star, which is Proxima Centauri. And that's another step of about 10 to the 5 or so. So the distance to Proxima Centauri is this in meters. But if you want it in AUs, it's 200,000 AUs, so it's 200,000 times bigger than the Earth-Sun distance, the distance between the Sun and Proxima Centauri. Or in terms of light travel time, it's 4 years. So when you look at Proxima Centauri, you don't see it the way it is right now. You're seeing it 4 years ago in the past. And if you wait for another 4 years, then you'll see it the way it is right now, but you'll have moved 4 years into the future. So even between stars, the distances, even if you start using AUs, they become a bit too messy to use because you get many powers of 10. And so people have introduced a new distance, it's called the parsec, and the abbreviation is PC. And the parsec itself is also an abbreviation. It stands for a parallax of an arcsecond. And this is kind of tied up in the history of basically astrology. I mean, that's where it came from, but if people want to talk about that, I can talk about that later. But the way this is defined is you take your observer and back her out very, very, very far away from the Earth-Sun system, so far away that 1 arcsecond at her subtends this 1 AU over here. And since this 1 AU is so huge and an arcsecond is such a tiny angle, if you go around a whole degree, a whole circle, there's 360 degrees, and each of those degrees you can split up into 60 arc minutes, and each arc minute you can split up into 60 arc seconds. So an arcsecond is a tiny angle, so this observer has to be really, really far away. And when she's at a position where this 1 AU subtends 1 arcsecond at her, she's said to be a parsec away. So this is kind of called a parallax. It's the distance between these 2 points, an angular distance. And if we were doing physics and using physics units, light takes about 3 1/4 light years to travel a parsec. So that's a really nice conversion factor. You just have to remember that a parsec is 3 1/4 light years. So people who study collections of stars don't use the AU or the second. Instead, they use the parsec as the length scale. So just to quantify this a little bit with things that you're probably more familiar with, the Earth-Moon distance is about 4 times 10 to the 8 meters. And in terms of light travel times, that's 1 1/3 of a second. We're in Kansas, so Pluto is still officially a planet. And Pluto's orbit is 40 AUs, the radius of Pluto's orbit. So in terms of light travel time, that's 6 hours. So this New Horizon pictures took 6 hours to come back to the big Deep Space Network telescopes. And the furthest we've sent anything are the 2 Voyagers. And these numbers are from their 40th anniversary in 2017. So Voyager 1 had gone 140 AU, so 19 1/3 hours light travel time. But when you convert it to the typical length scale you use to study collections of stars, it's not even 1,000th of a parsec away. So it's going at 3.5 AUs a year. And it's going to take tens of thousands, or maybe even 50,000 years to get to the nearest star if it's heading in that direction. So this is our little tiny solar system. I don't know if we could turn off all these lights, maybe this will look a little bit better, but it'll look even better if you go look at it on a computer. This is called the European Southern Observatory Milky Way Galaxy. So this is the collection of stars we live in. And it's really beautiful, but it's probably not that useful to use as a description of what's going on here. This is an older image of the Milky Way. You can see the quality, the change. And this is probably a better one. So we live in this collection of stars. There's probably about 200 billion stars. And it's kind of disc-shaped with the bulge in the center, so it's like a frisbee. If you looked at it from the top, you'd see the spiral arms, or from the bottom, and there's kind of a bulge in the center. So maybe we can start with the dimensions here. So the diameter of the disk is 50 kiloparsecs. So kilo is 1,000, so that's 50,000 parsecs. And if you want to turn it into light travel time, you take that 50,000 and multiply by 3 1/4. And you get 160,000 years, or 160,000 light years. So if you started over here and traveled at the speed of light, it would take you 160,000 years to cross this. And you can't travel at the speed of light. The only things that can travel at the speed of light are things that have no mass. So you can think about this 160,000 years and compare it to the 500 seconds between the Earth and the Sun, or the 4 years between Earth and Proxima Centauri. So this is a huge, huge object, but it's one little galaxy. So we live in the disk about 1/3 of the way out. There's a bulge in the center, central region, and there's a nucleus over here. And that nucleus is where our black hole lives. So we have a biggish black hole there. It's about 4 million times as heavy as the sun. But on the scale of black holes and galaxies, it's pretty puny. Most galaxies have billion solar mass black holes. So there's the disk, and you can kind of think about this guy. So these guys there's a bunch of stars. They have mass, and Newton tells you they're going to be pulling on each other. And so they're going to want to come really, really close together if there was nothing else going on. And the fact that they're in a disk tells you immediately there's something going on, and the fact that there's also a bulge here is telling you something's going on. Because they couldn't stay in a disk unless they had some other form of energy. And they have rotational energy, they have kinetic energy, and they're rotating in the plane of the disk. And it's like a satellite around the Earth, so if that satellite didn't have the velocity, it would drop, it would be pulled in by gravity, and the Earth would collect it because gravity is attractive. So you don't have systematic rotation for these stars over here. They're just kind of bouncing around randomly. But the disk, the stars in the disk are rotating systematically around the center of the galaxy. There's a few other things here. So there's this black stuff here. And this black stuff is not indicating the absence of stars. What it's indicating is the presence of dust. And this is kind of somewhat related to the stuff you vacuum up at home. They're small particles with silicates and stuff. And what this dust does, and you've probably noticed this when it's been a really dusty day, it scatters or it absorbs light. And if it absorbs light, light has energy, and you know that because if you go out in the sun, you feel warm. And if this dust is absorbing this energy, it's either going to get hot and explode, or it's going to re-emit some of that energy. And it's actually, mostly it's re-emitting that energy. And there's a fundamental law in physics that tells you when you absorb and emit energy, you kind of degrade things. So that's related to this phenomenon in thermodynamics. And light that's got longer wavelength has less energy than light that has shorter wavelength. So red light is less energetic than blue light. And so plumbers have got everything wrong in your sink at home. But red light has less energy, it's got a longer wavelength. Blue light has shorter wavelength, it's more energetic. So this black band is just telling you that the visible light, the stuff that you can see with your eyes, has been absorbed by this dust. But the light that it re-emits after it's absorbed this is a much longer wavelength, and you cannot see that with your eyes. But if you had an infrared telescope and you looked at this black region, this would be really, really bright, because this dust is emitting infrared light, which is longer wavelength than the light you can see with your eyes. There are also a bunch of little guys over here, and these are the globular clusters. There's a couple of hundred around the Milky Way. They're just orbiting the center of the Milky Way. And they're collections of hundreds of thousands of very, very, very old stars. These are the oldest stars we know. And you can kind of tell they're really old just by the fact that they're almost perfectly spherical. So gravity wants to collect everything together and kind of make things into a sphere. I mean, that's why the Earth is a sphere. It wants to minimize the energy. And these stars have been around long enough, and they've been pulling on each other long enough that they're arranged kind of in a ball. And you can see these if you know where to look, and I'm sure many of you have seen this. But these guys are going around the center. They're orbiting our galaxy in this thing that's known as the halo. And this halo is maybe 10 times as big as the galaxy in diameter. So it could be like maybe 1.5 million light years from end to end. And it's mostly made up of all the dark matter. And the globular clusters have probably been formed much, much earlier than our galaxy was formed, and they got pulled in by the gravity of the dark matter, and they started orbiting our galaxy. So this is one little galaxy. Here's the next big neighbor, and I'm sure all of you have seen this. This is Andromeda. It's also a spiral galaxy. You can see the dust lanes, you can see the spiral arms. And Andromeda is a little bit bigger in diameter. It's probably 200,000 years if you travel at the speed of light. These two guys are dwarf galaxies that are orbiting Andromeda. They're bigger than globular clusters. Andromeda also has a lot of globular clusters. And we have a bunch of dwarf galaxies too, but you can't see any with your naked eye in the northern hemisphere. If you go to the southern hemisphere, you can see the large and small Magellanic Clouds, and if you know where to look, you can see those with your naked eye. So Andromeda is, in terms of meters, that's how far away it is from us. In terms of light travel time, it's about 2.5 million years from us. So when you look at light from Andromeda, that was probably emitted either by some clump of hot gas or a star. And it's traveled in a straight line for 2.5 million years before it hit your telescope lens or telescope mirror, and you got a picture of it, or you're looking through the lens and you can see, or the mirror, you can see it, and it traveled 2.5 million years in a straight line. And that's kind of an interesting time scale for hominin evolution on Earth. So probably our most famous ancestor fossil was Lucy. She lived in Ethiopia 3.5, maybe 3.25 million years ago, which is around this time scale. And apparently she was afraid of predators, and she climbed a tree and apparently fell asleep in it and fell out of it and killed herself. But she did that 3.25 million years ago, a little bit before the light you can see from Andromeda hits your eyes now. So galaxies are these collections of hundreds to 200, 300, 400 billion stars, and they're very, very heavy. So sometimes when they come closer together or when they're formed near each other, they pull on each other gravitationally and they start orbiting each other. And they form what are known as clusters of galaxies. And this is a nearby cluster, it's the Virgo cluster. And every single spot of light you see here is a galaxy, and every one of those probably has 200 or 300 or 400 billion stars. I mean, it's just kind of, you probably see maybe 500, 600, 700 galaxies on this image, and so you can kind of get some idea of how big this object is and how heavy it is. Well, actually, sorry, it's 2,000 So the scale here is a few megaparsecs, and M stands for 1,000,000. So if you want to turn this into light travel time, if you take a few million, so maybe 3 million, you multiply that by 3¼ so that's roughly 10 million. And so if you travel at the speed of light, it would take you 10 million years to cross this. And so it's a pretty huge object, but there's many, many, many clusters of galaxies in the universe. And this guy's even better seen in a completely dark room, so I don't know if I can go to full screen. Is there some, if you just, you can just look at this guy on full screen with, yeah. So this is, if we go back to, yeah, that guy's gone, so that's great. So if we go back to our guy over here, so there's a lot of dust here, and the clearest view we have of the extragalactic sky is that way. And you kind of set up this this coordinate system, and you call that direction the North Galactic Pole, and this direction the South Galactic Pole. And so the picture I'm going to show you is this region over here, and it's kind of like you've got a wedge over here, and it's all the stuff in between it. And it was taken by these guys, Shane and Bertanen, at Lick Observatory. So Lick and Lowell were the two observatories that were first scientifically sighted, so they went and checked the atmosphere and the seeing and stuff before they built them. So this was when they had glass plates with emulsion, which was just a few years ago before you got CCDs. And so they would stick these to the focus and get these pictures and then develop them. It was also a few years before they had scanners and computers. So these guys, by hand, on paper and pencil, figured out the angular positions of 400,000 galaxies. And this is pretty much the North Galactic Pole. That's the Coma Cluster. Those few pixels, that's like 5,000 or 6,000 galaxies, each of them a couple of 100 billion stars. The map was made much later in the 70s. So you can see three kinds of structures here. You can see the rich clusters of galaxies. And if you look carefully, you can see darker regions. And these guys are called voids. And they're dark not because there's dust there obscuring the light, but they're dark because the bright galaxies aren't there. So the bright galaxies tend to hang out on the sides of the voids. And so you can see the filamentary structure. So there's kind of one-dimensional structures. And that's kind of the enhancement due to the bright galaxies. So the scale here is roughly 300 megaparsecs across at this distance from us. If you want to travel from one end to the other end, so it's 300 million, and then you want to multiply that by 3¼ to turn it into light travel time, and so that's about 1 billion years. So it would take 1 billion years to cross here, and you can compare that to the distance from the Earth to Andromeda, which is 2.5 million years, or the distance between the Earth and the Sun, which is 500 seconds. So this is a huge chunk of the universe, and it's got these three interesting structures, the bright clusters, and the voids, and the filaments. And an easy way to kind of visualize this is to think about bubbles in your bathtub when you're having a bubble bath. So the voids are the interior of the bubbles, and the bright galaxies tend to avoid them, and they tend to hang out on the surface of the bubbles. And where two bubbles come together, you're going to get a one-dimensional intersection of those two bubbles, and that's going to be enhanced. And those are the filaments, and so you can see the one-dimensional linear structures. And where a bunch of the one-dimensional linear structures come together and drain, you get the bright clusters. So this distribution has a jargony name. It's said to be very anisotropic. And so maybe we should start with the word isotropic first. So when you're looking at something and you say it's isotropic, that means it looks exactly the same in every direction you look, whether you look above you or below you or to your right or to your left in front of you or behind you. And you can do that in this room, and if you look above you, you don't see the same person that you see on your right, and you don't see that same person behind you. So this room is very anisotropic, and you can go that out to a whole bunch of scales. Topeka is very anisotropic. The surface of the Earth is very anisotropic. So if you get up high enough above the US, you look to the west, you can see the Rockies. You look to the east, you'll see the Atlantic. And you don't see the Rockies to the east also. You do that for the solar system. You look in one direction, you see the big sun there. And you look in any other direction, you don't see an equally big sun anywhere else. And the solar system's pretty anisotropic. The Milky Way is anisotropic. This distribution is anisotropic. You look over here, you see hardly any bright galaxies. You look over here, you see thousands of bright galaxies. So this is kind of not that unexpected. We've walked out on large scales and the distribution's anisotropic. But the thing that changes is that when you get out a little bit larger, the distribution becomes isotropic. It looks the same no matter what direction you look in. And this is a picture that was put together from data taken by the Planck satellite, which was launched by the European Space Agency. And it's a satellite that carried a bunch of microwave radiation detectors. And all of you are familiar with microwaves if you cook at home using a microwave oven, or if you've got a speeding ticket from a police officer. So what they're doing with that speeding ticket is they're taking a microwave source and they're bouncing those microwaves off your car, and they're collecting the reflected microwaves. And because your car is moving, there's the Doppler effect, and those microwaves that come back have a different pitch than the ones they sent out. And the difference between the two pitches is enough for them to tell how fast you're moving. And you're all familiar with the Doppler effect if you notice a siren, a car with a siren going by you. As it comes towards you, the pitch goes up, and as it goes past you, the pitch goes down. In terms of wavelength, as it's coming towards you, the wavelength's getting shorter and shorter, and as it's going past you, the wavelength's getting longer and longer. And so these are the measurements made by the Planck satellite. So what I'm showing you is the satellite went out to L2, and it looked out in all directions, and it had this microwave detector there, and so it could detect the pitch or the frequency of the microwaves or the wavelength. And we know from the pitch or the wavelength, we know the energy of the microwaves, and from that we can figure out the temperature of the microwaves. And so you can think of this as a big thermometer measuring microwave radiation that's coming towards you. So it's sitting out here, and it's measuring everything from the 4 pi solid angle that's coming towards it. I mean, there has to be some correction for the galaxy and stuff, but that's, I can talk about that later. And what I'm showing you is, so you can kind of think of being inside a big beach ball, and I sliced the beach ball from the North Pole to the South Pole, and I've opened it out and spread it out over here. So the North Pole of the beach ball is up there, and the South Pole is here, and if you want to close it up, you just pull this, stand over here, pull it around you, and cover yourself with it, and you're inside the beach ball. And this is squashed onto a flat plane so you can see it. So the blue spots are the hotter microwaves, and the red spots are the cooler ones. And they can measure the temperature, and so maybe the first thing you might be interested in, what is the average temperature across the whole sky? And if you do the average, you find it's about 2 3/4 Kelvin. So Kelvin scale is the absolute temperature scale. And at 0 Kelvin, everything stops except for Heisenberg uncertainty principle motion. So in this room right now, we're roughly at about 300 Kelvin. So 2 3/4 Kelvin is an extremely tiny temperature. So once you know that the average is that low, the next thing you might be interested in is what is the temperature difference between the hot spots and the cold spots. And you can go and measure that, and it's roughly 30 or 40 millionth of a Kelvin. So if we just use 30 millionth of a Kelvin, and compare that to the average temperature, which I said was 2 3/4 Kelvin. I'll just approximate that by 3 Kelvin. So the bumpiness is about 30 microkelvin, the average is 3 Kelvin. So you can divide the 30 microkelvin by 3 Kelvin to get some idea of how bumpy this thing is. And it's bumpy to 1 part in 10 to the 5, because 30 millionth divided by 3 is 1 times 10 to the minus 5. And in terms of percentage, that's 0.001%. So the temperature difference between here and here is 0.001%. So this is very, very isotropic. It's anisotropic to only a part in 10 to the 5. But if you go back over here, this is very anisotropic. So the scale over here is maybe a factor of 20 bigger than the scale there, which I told you the whole thing was 1 billion years to cross. So it takes about 1 billion years to cross here. So the bumpiness here is on scales of tens of millions of years, or even hundreds of millions of years. But when you get out to billions of years, it becomes isotropic. So these are two very, very, very important facts about the universe, about reality. Like locally around us, matter and light or radiation is bumpy, it's spatially anisotropic. But when you look out on much, much larger scales, matter and radiation becomes isotropic. It looks the same no matter what direction you look in. And I'm not going to really explain how people think about this now. I'll just tell you that the model that people use to make sense of this is called the inflation model of the very early universe. And that applies when the universe was maybe 10 to the minus 33 seconds old. We're roughly 13 3/4 billion years old now. And you can read about this, but you've got to be careful what you read, because there's a whole bunch of garbage on the web. So you're going to have to look carefully. Wikipedia is usually pretty good. Scientific American or Physics Today or Discover or Astronomy, any of those, and look for inflation model of the early universe, and you can see how people think about this now. So the inflation model makes predictions that are consistent with what we see, but not at a level where we can really test them at present, because our measurements are not accurate enough to rule it out. And so most people think it's true, but we don't know yet for sure. Okay, so those facts were bizarre enough, at least the second one. This is even more bizarre, that the universe expands. And so when you say that something's expanding, you're immediately implying you have a measuring device that's not also expanding in exactly the same way. Because if your measuring device was expanding the same way, you'd never notice the thing was expanding. And so it's kind of really useful to understand how our measuring devices work and how the universe works. So if you think of a meter stick or a foot rule, that's kind of held together by electromagnetism. And the other really important force on these large scales is gravity. So if I have a small mass like my keys, and there's a big mass, the Earth here, if I don't support my keys, then they're going to be pulled towards the Earth, and the Earth's going to be pulled towards my keys. So the Earth moves a little, the keys move a lot more, and the Earth moves only a little because it's much, much heavier. But gravity is attractive, so if you have two masses, they get pulled together, and that always happens under gravity. And we know the law that applies there. It's called Newton's inverse square law for gravity. So if you take these two masses and you double the distance, then the gravitational force goes down by a factor of 4. If you triple the distance, the force goes down by a factor of 9. That's 3 cubed. And so it's an inverse square law, but it's attractive. The other force that's important is the electromagnetic force, or the electric force. And for that, we have two different kinds of charges. You have negative charges, and an example of that is the electron. And you have positive charges, and an example of that is the proton. And the electromagnetic force is also an inverse square law force. And that law is called Coulomb's law. So if you double the distance, it either goes down by a factor of 4 and so on. And the difference between electromagnetism and gravity is that in electromagnetism, the like charges repel, they're pushed apart. So if you have two protons close together, they get pushed apart. And if you have two electrons close together, they get pushed apart by the electromagnetic force. But if you bring a proton and an electron together, unlike charges are attracted. So electromagnetism has an attractive part when the charges are not the same, and it's a repulsive part when the charges are different, when the charges are the same. So gravity is always attractive. Gravity pulls stuff together. So we have to think about our meter sticks. So our meter sticks, they're made up of molecules, but I guess it's easier to think about this in terms of atoms. So an atom has this electron cloud, and as you go to the center of the atom, there's a nucleus on a scale that's maybe a factor of 10 to the 4 smaller, and between that there's a bunch of empty space. And because we're made up of electrons and atoms, and we have charge and we have mass, so I guess the first thing we have to think about is whether we're affected by gravity or whether we're affected by electromagnetism. So if you're sitting next to someone, are you pulling on them electromagnetically? Or are you pushing on them electromagnetically or repulsing them? So how many think you're pulling on your neighbor through electromagnetism? How many think you're pushing on your neighbor through electromagnetism? So two for pushing, and nobody else, no one for pulling, and the rest of you are just really, really shy, or?
Mainly gravity.
What about gravity? Are you pulling on your neighbor gravitationally? Yeah. So you're not pulling or pushing on your neighbor electromagnetically because the way atoms are made up, right? So they have electron cloud that has a certain number of electrons, and you have exactly the same number of protons in the nucleus. So the protons have the positive charge, the electrons have the negative charge. So your electrons are pushing Doug's electrons away while they're pulling his protons to you, and so they're canceling out. And so you're basically neutral, unless you biked in here or you vigorously combed your hair before you came in here and built up some static charge. So otherwise, bulk matter is neutral, and you're pulling on your neighbor gravitationally, but your masses are really tiny, and the gravitational force is proportional to the product of your two masses. And if you scaled up your masses to the masses of planets, you'd pull on each other much, much stronger gravitationally. But the really interesting thing is these forces, the gravitational force and the electromagnetic force, both obey inverse square laws. So you can bring two protons next to each other, and they have positive charge, so electricity is going to push them apart, but gravity is going to pull them together. And so we can go and calculate the ratio of those two forces. So has anybody thought about or read about how strong electromagnetic repulsion between two protons is compared to gravitational attraction? I mean, is it much stronger or much weaker? Electromagnetic repulsion is much stronger. It's 36 powers of 10 stronger than gravitational attraction. So electromagnetism is an extremely strong force. So when you get down to objects like your meter stick, that's made up of atoms, and those atoms, they hang out next to each other, the electron clouds hang out next to each other, and those electrons hate each other, and so they want to push apart, but they have neighboring atoms and behind them, and those neighboring atoms, electrons, also hate the electrons of the other atoms. So these electron clouds have nowhere to go, and it's because the electrons kind of repulse each other because of Coulomb's law, the atoms can't move, and that's why matter is rigid. And I mean, that's kind of a really interesting thing to think about, because you just have this electron cloud, and inside of it, you go down by 4 orders of magnitude in distance, and you get to the proton, but inside of it's empty space. So you're basically empty space. The chair you're sitting on is empty space. And so in principle, you should be able to just fall through that chair or walk through walls because walls are empty space. And the reason you can't do that is because your electrons hate the wall electrons and they bounce off each other. And that's what gives matter rigidity. But when you get up to larger and larger scales, if you talk about two planets next to each other, there's no electromagnetic force between them, and gravity, even though it's a weak force, because the mass is so big, it becomes a dominant force in the scale of planets. And then you go up to galaxies. Galaxies are much more massive, and gravity becomes even stronger between pairs of galaxies if they're close together. So in small scales, the stuff that's holding your meter stick together is electromagnetic force. But on large scales, gravity completely dominates what's going on. Electromagnetism is irrelevant. And that's kind of a really important thing to know, that on large scales, gravity dominates, and at small scales, electromagnetism dominates. So gravity can't affect your meter stick. It doesn't move atoms around in it. So if you want to talk about cosmology, you've got to use the best model we have for gravity, because that's the relevant force on those huge, huge length scales. And the best model we have for gravity is Einstein's theory of general relativity. And that's not an easy theory to appreciate unless you kind of do the math, because you don't have any intuitive feeling for what it says. I mean, we can kind of say this in words, but I'll just start out with Newton's description of reality. So Newton kind of said there's a fixed space and a uniform time, and he could collide his balls in that space and bounce things around. And Einstein realized that there are times when that's a really bad description of reality, and that happens when things are moving at speeds close to the speed of light, or you have really strong gravitational fields. And he realized you could get a better model where you allowed space and time to respond to what was happening around it or in it. Like when these balls were moving, space would respond and time would respond, and time and space would change. And first he came up with special relativity, then he came up with general relativity. And to get a good idea of general relativity, you have to solve his equations. There are a couple of partial differential equations, and you can kind of turn this all into English and talk about it using words, but it's an inaccurate translation. But I'm going to try to turn this all into English and say it all in words. So what happens is that when you go on to really, really large scales, general relativity wanders around in the universe, and it comes to regions where there's less mass than on average. And what it does there is it creates more space. And that space has to go somewhere, and it spreads out. And everything lives in space, so everything that's embedded in that space as it's spreading out gets taken along for the ride. So I'll start out with a couple of cartoon demonstrations. So I've got an exercise band here, and you can kind of think of this as a one-dimensional universe, because all I have to do is kind of mark off tick marks here, and you'll know how far you are along it. And what I'm going to do is put an electromagnetic, or just put a wave on it, and you can see the peaks and troughs. And if I had an extra pair of hands, I'll get my meter stick, and it's held together by electromagnetism. But general relativity is going to create more space. And what it does is spreads things out, and the universe expands. And as it does that, you can see a meter stick is not affected because it's held together by electromagnetism, which is a way, way, way stronger force than gravity, which is doing the stretching. But you can see that the wave lives in this space, and its wavelength, the distance between two peaks, it gets bigger and bigger as the universe expands. So if you start out with short wavelength blue light, and let the universe expand, it becomes red, redder, and redder, and redder. And if the universe contracts, red light becomes blue. So this is not accurate in a couple of ways. Gravity is not going to the ends or the edges of the universe and pulling. It's going into space. General relativity is going into space and creating new space and pushing stuff out. And this doesn't happen in one dimension, it happens in every dimension. So we live in a three-dimensional space, and this room is a three-dimensional space. And you can tell that by setting up a coordinate system. So you can put up one vertical axis there and two horizontal axes here. And if you wanted to know where Jan was, you'd have to measure along from the origin up to there, along the x-axis, then along the y-axis. From the origin, if we set the origin here, you'd measure along here up to here, and then along the z-axis if you want to go to the top of her head. And so you'd need 3 positions, and that will tell you where the top of Jan's head is. So it's a 3-dimensional space, and this is a 1-dimensional space because I could just mark, well, it's really 2 dimensions, but I'm kind of ignoring this dimension, but it's 1 dimension, and I can just mark off along here. So that's the expansion of space, and this is it with a little more math. So I'll start out with the hands kind of closer together, and then I'll stretch the band, and it gets larger. And I've put a wave on it, and it's got a wavelength here. So this is when the light was emitted. That's the wavelength when the light was emitted. And as time goes on, the wavelength gets stretched, and it becomes redder and redder. And we've got to have some way of comparing ages and times and length scales. So people kind of introduce what's called a scale factor, and a very rough way to think about that is to just think about the distance between the hands. And as time goes on, that gets bigger and bigger. And the usual symbol for a scale factor in cosmology is the variable a, and it's a function of time. So let's look at what time is doing. So as you go back, you're going back to the baby universe. So time runs positively this way. It gets bigger and bigger this way. And the scale factor, the size of the universe, because it's expanding, it gets bigger as you go forward in time this way. But astronomers don't like using these variables. They use a different variable, which they call the redshift. And the way to think about that is to think about the wavelength, this is lambda. And as time gets older, as the universe gets older and older, the wavelength gets bigger and bigger. And it's really easy to convince yourself. I mean, you can do this, take one of these exercise bands and take this and just stretch it, and you'll see that the wavelength is proportional to the size of the exercise band. It's proportional to the scale factor. So as you double the size of the universe, the wavelength doubles. As you triple the size of the universe, the wavelength triples. And astronomers kind of prefer this variable, which they call z. They don't use variable a that much. And the way this variable is defined is as 1 plus z is the scale factor of the size of the universe now divided by the scale factor of the size of the universe when that light was emitted. So if we emit the light right now, at the time where we live, a of t would be a of now, and a now divided by a now would be 1, and that 1 would get rid of this, and the redshift is 0. But as you go back in the past, a t gets smaller than a now, and a of t is in the denominator, so this quantity gets bigger than 1, and so z increases away from 0. So the redshift gets bigger as you go back in the past. The time gets bigger as you go forward. The scale factor gets bigger this way, but the redshift goes the opposite way, and that's the variable the astronomers use. So I guess there's a couple of other things. So we know the universe is expanding, or maybe I should talk about this guy first, which is this telescope. This is the other famous observatory, Lowell Observatory. It's in Flagstaff, and you can go see his telescope, and you can go see the chair he sat in where he was doing his observing. This is Slipher, and so Slipher was looking at galaxies outside the Milky Way. He's collecting light from them and passing them through diffraction gratings and breaking it up into its spectrum. And he realized that he could identify the atoms that created this light because he could take ratios of the wavelengths of spectral lines. And those are characteristics of individual type species of atoms or molecules. But the individual wavelength for each of those lines was longer than the wavelengths he could create with exactly the same gas in his lab. And so you see this red shifting. And he found this in 1912. And if you want, we can talk about later why he was doing this, but it was basically to study intelligent life on Mars. But so there's two ways to think about this. So maybe Slipher was at the center of the universe. There was this huge firecracker, and everything went away from him at some time in the past, and he just happened to be at the center of the universe, and so he saw everything moving away. Just like if you had a whole bunch of police cars around you in a circle, and they all headed away from you with their sirens on, you would see the red shifting, or you hear the red shifting. But that's not what's happening. It's something much more interesting that's happening. And this is kind of another cartoon description of what's going on. So this is a flat universe. It's a three-dimensional flat universe because there's three axes here. And clearly it can't be the whole thing, because if it was, and I went to the edge and looked out, I wouldn't see the same thing as when I looked in, and it wouldn't be isotropic. And so that's telling you, if you want a flat universe and you want it to be isotropic, you've got to send it out to infinity in all three dimensions. Because if you send it out to infinity, there's no edge, and you can't go to that edge and look out and see that it looks different, because there isn't any edge. And so we're going to let the cake expand, and we've got to remember that's just a chunk of the universe. And we'll put our observers on each of these, and those are the individual galaxies. So maybe the first thing we have to talk about is where the galaxies actually expand. And galaxies, after they've been formed, they're like the ping pong balls here. What's expanding is the creation of space between them, but the size of the ping pong balls are not changing. So the Milky Way is not changing, Andromeda is not changing. Once galaxies are formed, they don't change, but when they're forming, then life is a little more complex. So we'll put our observers on here, and we'll ask our observer number 2 what she sees. And she's going to tell you she sees every single chocolate chip move away from her, no matter what direction she looks in. And we'll put an observer number 4 and ask him what he sees, and he's going to tell you he sees every chocolate chip move away from him. So the fact that Slipher was seeing all these things moving away from him didn't mean that he was at the center of the universe and there was a big explosion there previously. This is actually what happens. Every point in space starts moving away from every other point in space. So the Big Bang, I mean, even at the Big Bang, space was probably infinite. And at that instant of time, or even probably before that, but so when we just talk about the Big Bang, we'll say that that's the origin of the universe. And at that instant of time, every point in this infinite space moved away from every other point. And that's the expansion of the universe. And we can kind of look at this balloon demonstration. I mean, I guess Doug has insurance, so So I put the galaxies on here, and these are the red things I stuck on, because the galaxies don't expand with the expansion of the universe. And so we can put ourselves in one of these galaxies and think about what's happening. So you've got to just think of yourself as an ant. All you can do is walk on the surface of this balloon. There's nothing outside here, there's nothing inside, and all you can do is walk on the surface, and there's really no neck here. So if you're on this galaxy here, as time goes on, space gets created between this neighboring galaxy and you. So if this guy sends you some blue light, or there's an atomic transition and it emits blue light, that blue light will travel here, and it takes some amount of time to travel because light travels at a finite speed. And while it's traveling, its wavelength is going to get stretched. So even though it started out blue, it'll be slightly purplish there. But if you look at this guy over here, it takes longer for this light from here, the same blue light, to reach you, so it'll be even redder. And if you look at this guy here, it's going to cover much more space to reach you. So that light's going to be even redder. So that's the expansion of the universe. Every point moves away from every other point, so you're not sitting at the center of the universe anywhere. So if you were here, you'd see every galaxy move away. If you're here, you'd see every galaxy move away. If you're here, you'd see every galaxy move away. So So this is a two-dimensional universe. All you need is you can set up the same latitude and longitude coordinate system you use on the Earth, and you just need 2 coordinates and you can tell where you are. And it's a compact universe, it's a closed universe, so it doesn't have any edges, so it can be isotropic, unlike a flat universe. So the equivalent of a two-dimensional flat universe is the top of this table, but if you went to the edge and looked out, it would look different. And so you've got to send the edges out to infinity for it to be isotropic. You don't have to have an infinite positively curved universe, it can be compact. So that's the expansion, and the next step came, the guy who really established the expansion was Hubble. So Hubble had a much better telescope. Yes, that's the 100-inch on Mount Wilson, which you can also go and see now. And this guy next to him, that's Humason. So Humason dropped out in 8th grade, and he got a job as a mule skinner, and those are the guys who lead mule teams. And there were no roads going to the top of Mount Wilson then, so he kind of carried up a lot of the equipment they needed to build Mount Wilson up the side. And he was out of a job when they built the telescope. And there was an opening for a janitor in the observatory, so he took that job. And Hubble got to talking with him, and he realized Humason was really intelligent, and he got him to repeat Slipher's measurements of the redshifting. So Slipher used the Doppler formula, and he could measure from the redshifting of the spectral lines how fast these galaxies were moving. And Hubble had this bigger telescope, and he could start resolving individual stars in these galaxies. And he realized that he could see Cepheid variable stars in some of these galaxies. And Cepheid variable stars are extremely useful because of a relation that Henrietta Leavitt had discovered. So she was what was known as a computer. So she worked at the Harvard-Smithsonian Center in Cambridge, Massachusetts, and that was one of the places where these big glass plates would get sent to so they could store them. And some astronomers, not all of them, just maybe a few, are kind of a little bit obsessive, so they take pictures of the same region of the sky over and over and over and over and over again. So she had access to the same region of the sky at many, many, many different intervals of time. And she realized she was seeing pulsating stars in there. And she looked at some of the nearby ones. So Polaris is a Cepheid also. And they pulsate, and she could measure distances to the nearby ones using triangulation. So once you get the distance, and you have a photometer, and you collect energy per unit area at your position, you can figure out the wattage of the star from the distance and your photometer readings. So she could figure out the wattage of these stars, and she did this for a bunch of nearby Cepheids. And she realized that the pulsation period was related to the wattage of the star. And so if you can measure the pulsation period of the star, you can get the intrinsic brightness of the wattage. And once you know the wattage, you can then use the inverse square law for radiation intensity and get the distance to the star. So Hubble found these Cepheids in these galaxies that Slipher had looked at, and he could measure distances, and Humason redid the velocity measurements or the speed measurements, and you got this relation that the recession velocity of a galaxy is proportional to how far it is from us. So a galaxy twice as far away would move twice as fast, a galaxy 3 times as far away would move 3 times as fast, and so on. And because astronomers are strange and they measure distances in megaparsecs and recession velocities in kilometers per second, this constant of proportionality has very, very strange units, but it's really simple to think about because this is distance over time, this is distance, so the two distances cancel out, and you have 1 over time, or time in the denominator. So the Hubble constant has units of 1 over time, or dimensions of 1 over time, and it's roughly, in a very loose sense, the inverse of the age of the universe. But but it's not that accurate. You have to be a little bit more careful. But it's constant of proportionality because this is kilometers per second, that's megaparsecs. The units of this is kilometers per second per megaparsec. And this is kind of my favorite range of values for it. So this guy is called the Hubble law. And you can see data that supports it. So this is from the Hubble Space Telescope Key project that was led by Wendy Friedman. This was one of the reasons the Hubble Space Telescope was built, was to get above the Earth's atmosphere and try to get rid of atmospheric issues and see further away. And so what you're seeing over here is the recession velocity in kilometers per second, 10 to the 4, 2 times 10 to the 4, 3 times 10 to the 4. And you can ignore this residual panel down here. These are the distances to the galaxies. So this one's 100 megaparsecs away, so you go up over here, and it's moving away at about 7,000 kilometers per second. 200 megaparsecs is moving away at about 14,000 kilometers per second. And this was the best fit line, and this is the Hubble constant. This was in 2001. And more recently, I think it's come down a little bit, so it's more like 68 or so. So it's a straight line, it fits really well. The recession velocity is proportional to distance. So the further away the galaxy, the faster it's moving, and that's just the Hubble law, and that's the expansion of the universe. That's just this law. V is proportional to R. It's a linear relation. And that's the expansion of the universe. So I don't know, how long do you want me to go? Because I probably have about another hour to cover, but maybe I should just come back later and do that again. So
We'll have to quit it at a quarter till.
Okay, so do you want to just have questions, or?
Yeah, when I took courses at Washburn on the theory of relativity, we talked about the light cone, that there was a point where we could never get any information. So doesn't that limit how we could conceptualize how large the universe is?
Yeah, so the universe, so let's just ignore the expansion for a second. So we know the universe is 13.75 billion years old. So if you send a signal at the speed of light, you can see 13.75 billion light years. And that's about all you can see. So the fact that there's expansion means that you actually have to do an integral to figure out how far you can look. And because things were closer in the past, you can actually see, depending on what cosmological model you assume to do that integration, you can see 30 or 40 billion light years. So that's all you can see. It's a really tiny patch of the universe. And I mean, so we kind of make this assumption that everything out there is, we don't live in a special position. So maybe I'll just talk about this right over here. So we know that the universe is spatially isotropic, at least from our point of view. And it would be kind of strange if you called up your friend on Andromeda and asked her whether it was spatially anisotropic there or was spatially isotropic. And she would probably tell you it's spatially isotropic. So what you've done when you've done that is you translated yourself in space, and you looked around again, and it looks exactly the same in all directions, provided you're looking at large enough length scales. And that's telling you, because of a theorem in geometry, that you live in a distribution that has much, much more symmetry than actual just spatial isotropy about one point. And that symmetry is called homogeneity. You translate yourself in space and it looks the same. And you're very familiar with this. If you have a gallon jug of milk, all you've got to do is buy a scuba suit and jump in it and swim around. And it looks exactly the same white, no matter where you are, provided you don't get to the edges. That's a homogeneous distribution. And that has much more symmetry. And so homogeneous means it's the same no matter where you are. So it could be that we're sitting in the center of this big bubble whose radius is 40 billion light years. And the moment you get beyond it, everything changes dramatically. That's where the dragons live. But that would be kind of really strange, because you look around you and it looks isotropic, and we can measure homogeneity, and it's approximately homogeneous around us. So it would be really strange that if it was that different elsewhere. And we've always had this problem with astrophysics. I mean, when people realized that stars were really, really far away, they said that we'd never understand them. And people later on realized that stars were made up of the same substances we were made up of. We were made up of atoms, they're made up of atoms. And you study atoms enough, you can get spectral lines, you can identify what atoms are there. And so even though you can't go to those stars, you can tell what they're made of. And so even though you can't see this stuff, I mean, it would be kind of strange that it would be completely different than what's around us. And we can only see a tiny bit. And the things that are even stranger is if you go back over here, this line just rises, it keeps going, it's an exact law. So at some point, you're going faster than the speed of light if you go far enough. And almost everything in the universe is moving away from us faster than the speed of light. And that's consistent with relativity. You can make stuff move faster than the speed of light. It's not that difficult. And I mean, if you don't believe that, I can show you a demonstration, or at least a thought experiment. I mean, so are people familiar with the fact that you can make stuff move faster than the speed of light? Or, okay, well, you can think about it. I won't do this, but if I had a laser pointer here and I kind of just ran it on the ceiling, there'd be a dot moving up here. And if we were lucky, it would be cloud covered, and if there was no ceiling, that dot would be moving much, much faster on those clouds. And if the moon was overhead and I flicked it fast enough, that dot would move faster than the speed of light on the surface of the moon. So you could get stuff moving faster than the speed of light. It's just not sending a physical signal. I mean, you can't send a physical signal faster than the speed of light. So these galaxies, I mean, they don't come along with individual rockets strapped to them and those rockets moving them around. So it's space that's being created, and that space is just spreading out, and it's taking the galaxies along. And if they're far away enough from us, they're moving away from us faster than the speed of light. And they send us signals back at the speed of light. So at some point, they're moving away faster than the speed of light, and we'll never get those signals. And that's why we can only see a finite patch of the universe.
Hubble's Variable Nebula, for one. That's a good example of it also, because the cloud structures are moving back.
So you can get, in some quasars too, you can see this, depending on how it's pointing towards you.
Then there was that other paper or whatever that came out recently on dark matter, dark energy being generated by black holes.
Yeah.
I don't see that.
Yeah, I couldn't really understand that. I read it a bit, and I'm not sure what they're trying to say, but...
Yeah, because gravity, when you're dealing with supermassive black holes and stuff, is the ultimate crunch. And gravity in itself is an attractive force. It's not a repulsive force as in dark matter or dark energy.
Yeah, I haven't really got to dark energy yet, but maybe I should just come back in a couple of months or next year or something.
Professor, I have one question.
Yeah,
So you said like space is like expanding.
yeah,
So there are two curiosities, like what it is expanding into, and
Yeah.
the other thing is like, we know like energy density is like constant for space, so it must take energy from somewhere, like how we resolve this issue.
yeah. So it's not expanding into anything. There's nothing out there. Most likely the best model we have now is infinite, and it's flat in 3 dimensions. And every point is moving away from every other point, so there's nothing for it to expand into, and that's the universe. And actually, the energy densities are not constant, they decrease in time, and so I haven't got to that part, but I can talk about that if people want. So let's just go back over here. So because this is a much more powerful symmetry, this homogeneity, that makes it possible to look at just 3 different models, and these are the flat, open, and closed models. So I can't draw the 3-dimensional analogs, but I'll suppress 1-dimensional space and draw the 2-dimensional analogs. So we talked about the closed one, just the surface of the balloon, and the flat one's the top of the table over here. And this has zero curvature, this has positive curvature, that's the curvature that's greater than zero. And opposite to this, you have the open one, and that's the saddle-shaped one, and that has negative curvature. And it's going to go out to infinity in both dimensions. So we can kind of think about what the physics is. So we have roughly the size of the universe, or the radius, and as time goes on, it gets bigger and bigger, and that's sort of the scale factor. And Einstein's general relativity gives us an equation for the scale factor. And because everything's kind of dominated by gravity, it's the mass you have that affects the expansion of the universe. And because we have the possibility of an infinite universe, you don't want to deal with the total mass. So what we could do instead is kind of go to something like this and think about a little region here and count up all the mass you have in it. And that'll give you the gravitational field in that little region. So we'll deal with mass per unit volume or mass densities instead of dealing with the total mass. And that's the symbol rho, it's the mass per unit volume. You just add up how many kilograms you have in your little box and divide it by the volume of your box, which is L cubed. So we know, so a dot means rate of change, so it's the speed. So the scale factor is a dynamical variable. And the rate of change of the scale factor with time is the expansion speed or the expansion rate, and it means dimensionless just by dividing the speed by the scale factor itself. And we know this is positive because things are moving away from us. So the universe is expanding, things are moving away from us. And the next question we might want to ask is whether the person powering the universe, whether she has her foot on the gas pedal or the brake. So you're starting out, you have the Big Bang, and does she hit the gas and then it starts accelerating, or does she hit the brake and it starts decelerating and eventually stops and maybe it'll come back and recollapse on itself? And the easy way to think about this is to use an equation. So I've got this one equation here, and this equation is very, very, very similar to Newton's F equal to ma. And except I'm writing it in a form where it's A equal to F over M. And it's really, really unfortunate that A is acceleration when you talk about F equal to ma, and A is the scale factor when you talk about cosmology. But that's kind of historical notation. So all the A's I have here are the scale factor, so you can kind of think of it just as the radius of that balloon. And as time goes on, it gets bigger, and we want to know whether it's going to hit a maximum size and come back or not. And the acceleration is the two dots on top. It's the rate of change of the rate of change of the scale factor. So this is the acceleration, and this is the force side. And obviously the gravitational force, so you have Newton's big G, and then you have masses, mass per unit volume, so that's rho, and it's rho matter, so ignore this part for now. And we'll ignore this part for now also. So we'll just look at this guy, and there's a minus sign over here. And this minus sign is relatively easy to understand. If you think about what's happening between two of your nearby galaxies. So these guys have mass, and Newton's going to tell you they're going to pull on each other because that's an attractive force. But Einstein's going to want to create space between them because there's not much mass there. And so that part of gravity is going to try to push stuff together, Newton's going to try to pull stuff together. So if you put down a lot of galaxies, Newton's eventually going to win on small scales, and it's going to pull stuff together. And that's what this minus sign is coming from, that you get this thing expanding, it's starting out to expand, and somebody's put her foot on the brake, and so you get a deceleration or a negative acceleration. And the masses there's too much mass, and they're pulling back on each other, and they've stopped Einstein's space creation process, and it's going to start contracting. So you understand that. The next thing is to add this guy on here. This is the pressure, and if I was using more conventional units, there would be the speed of light squared in the denominator, and that immediately tells you this is an effect associated with relativity. So what this guy is measuring is the rest mass energy of those galaxies. But galaxies are pulling on each other and they're orbiting on each other, and so they have energy of motion. And Einstein tells us whenever you have an energy, E is equal to mc squared, there's an equivalent mass. So if you have kinetic energy, that will have an equivalent mass, and you have a gravitational field, it'll see that mass, and that kinetic energy will create a gravitational field. So even things that are moving create gravitational fields beyond just their rest mass energy. And that's what we call the pressure here. This is not the way you use the word pressure colloquially. So when you're using pressure in everyday life, you're actually talking about a pressure difference. So the balloon's expanding because of the pressure difference between the outside and the inside, and it's not expanding because of the pressure. The pressure is causing the increase of pressure inside is causing that pressure gradient. But so if you have moving galaxies, then you're going to have even stronger deceleration. So you're really, really happy, and you go tell your astronomer friends that you predict that the universe is going to decelerate, and they should go measure this and confirm it. And they go measure it, and they find that it's actually accelerating. And so you have a problem. So you can either say Einstein is wrong and we should throw this equation away, and then we don't have a problem, we don't have a theory, so there's no problem, you don't have a problem explaining observations. But if you want to be a little bit more conservative, and you know that Einstein's general relativity is both for black holes and it's both for the cosmic microwave background, you might want to try to patch up his equation. And one way to patch it up is to introduce a new substance, which is this piece over here, which is called the cosmological constant. And we see examples like this in the lab. So one example is what's known as the Casimir effect. That's C-A-S-I-M-I-R. And you can read about this. So it's when you take two conducting plates and you bring them very, very close together, they feel a force between them because of Heisenberg's uncertainty principle. And the same thing happens with the hydrogen atom when you use the correct description of the nucleus to do the quantum mechanics, and you get something known as the Lamb shift, which is a splitting of some of the spectral lines in the hydrogen, and you can see this observationally. So the hope is that you find a substance like this on cosmological scales, and it has a relation between its pressure, P, and its energy density, and it's a negative relation. And so you go back and look at this P, rho plus 3P here, and the P here is minus 3 rho. So this thing is just minus 2 rho lambda. And if you can get rho lambda to be much bigger than rho matter, this negative piece can overwhelm this positive piece and make everything in here negative. And that negative sign can cancel this, and then you'll get acceleration. So dark energy is a substance you introduce to give you accelerated expansion from Einstein's cosmological equations. And I mean, it would be a crazy thing to do, except when you measure this using half a dozen different techniques, you get roughly the same amount of dark energy. So it seems to hold together consistently, and maybe future observations will help us pin it down much more accurately. But that's what dark energy is. And maybe we should stop if you have to get out of here in 6 minutes.
Well, I think the library closes at 9, right? So
Yeah.
they start-
They start telling you.
They
that.
start coming across.
Okay, so maybe I'll be happy to answer questions if people have questions.
I actually have one.
Yeah.
It's on one of your previous slides.
Yeah.
Going back a little bit. Let's see. Go back. There.
Yeah.
So you have you talk about for adiabatic expansion. I mean, I'm familiar with adiabatic processes in the atmosphere.
Yeah.
Is that because the universe is expanding the universe?
So adiabatic is used in a slightly different sense here as in 2 time scales. So if you think about the expansion, the doubling time here, the time scale there is about 13 or 14 billion years. And that's something like half an exasecond. And if you think about the time associated with these guys, it's femtoseconds. So this 30 or 33 orders of magnitude difference between the expansion time scale and the time scale of the waves.
Okay.
And so you can't pump energy from one to the other because these time scales are so separate. And that's why the expansion happens this way. I mean, another way to think about it is you think about a closed universe, just a circle, and you put a wave on it. And as the universe gets bigger and bigger, if you could pump energy from the expansion of the universe to the wave or vice versa, you could affect the wavelengths and the number of zero crossings. But because these timescales are just completely separated, the number of zero crossings is the same no matter how big the universe is. And the only way you can get the number of zero crossings as you go around to be the same is for the wavelength to expand.
Yes. Are there more questions?
Are there any, so once I was in India and I was into a lecture like this, and there was one professor from BHU. He said like they were working on neutrino oscillations and wind particles, and they were saying that these are the most prominent candidate for dark matter.
So neutrinos, if you look at neutrinos as they come from us, from the sun to us, you can do measurements and you can figure out. So we have the three species of neutrinos, and they're related to the three lepton species. So we have the electron, which everybody's familiar with, and the electron has a cousin called the muon, which is about 200 times heavier, and it has another cousin called the tau, the tauon, which is maybe about 2,000 times heavier. And neutrinos come in the same kind of ratio. There's the electron neutrino, the muon neutrino, and the tau neutrino. And we can figure out what neutrinos are emitted by the sun. And we find that as they propagate towards us, the electron neutrino turns into the muon neutrino, and it depends on how far it travels. So the only way that can happen is if neutrinos have masses. And we can measure mass differences now. We can't actually measure individual neutrino masses, but we know that there are two mass differences that are non-zero. So there's got to be at least two of these three neutrino species that have mass. And neutrinos interact extremely weakly, so they behave exactly the way you expect dark matter to behave. And so we know that there's two neutrino species that behave like dark matter. Unfortunately, they contribute so little that most of the dark matter can't be made of neutrinos, so there's going to be other stuff also.
Other questions? Well, let's thank our speaker. I could definitely see a part 2 to this at some point.
Endless.
You mean I haven't confused you enough yet?
Well,
Nope,
I am confused, but then that makes it interesting to get
it
unconfused.
makes sense right now, but by tomorrow.
All right, well, thank you, everyone. And by the way, if any of you are basketball fans,
Yes, we
K-State
won.
won.
Yes.